Hi everyone, my name is Laura and today I'm going to present the progress of my graduation project presented for the degree of microbiologist. It is named as Polymeric microencapsulation of the fungal enzymeLaccase through microfluidic systems for its potential use as biocatalyst in wastewater treatment. First, as context, we know that most human activities that use water produce wastewater, and as the overall demand for water grows, the quantity of wastewater produced and its overall pollution load are continuously increasing worldwide. So, wastewater treatment has become an important worldwide priority during the past decade because if wasted water is not properly treated, it may negatively impact the environment and the human health, thus turning into a costly problem to most governments and countries. So conventional wastewater treatment technologies cannot eliminate these pollutants completely from the water. So enzymatic treatment arises as an alternative method for the treatment of organic micropollutants. There are multiple methods of enzymatic immobilization, such as physical absorption, chemical binding, polymer entrapment, and microencapsulation as the most used ones nowadays. And microencapsulation, for example, provides an efficient route to protect or isolate substances from harmful environments, and hence serving as a viable solution for oxidative degradation, for example. Moreover, the encapsulated substances can be released in a controlled manner without significantly altering the properties of the core materials and thereby maintaining their specific functionalities. However, microcapsule manufacture include some challenges like the precise control of morphology, size, distribution, and porosity of the shaped materials, which results in an inherent complexity during the scaling up process of such manufacture methods. So that is why some recent studies have suggested that droplet-based microfluidic systems offer a more controlled reaction environment and the chance to reduce the amount of reagents required for manufacturing, and thus providing an inexpensive manufacture process. In this sense, the main goal of this project is to establish the Laccase encapsulation efficiency and its enzymatic activity in different pH and temperature conditions in order to determine its potential use as a biocatalyst in the wastewater treatment. And also, the specific objectives are to design and manufacture the microsystem based on the foundation of two-phase interaction designs for droplet generation, and to set the pertinent parameters for the microcapsule generation in order to determine the maximum manufacturing efficiency, perform the microencapsulation of Laccase and assess the relevant enzymatic activity test, and also carry out the preliminary test using the microreactor to establish the potential use of this technology as an efficient wastewater treatment. Now, the methodology of this project can be divided in 8 different steps. So the first one is going to be for the microsystem design and manufacture for capsule generation. The second one is going to be the parameters configuration for microcapsule generation. And the third one is going to be the Laccase encapsulation and also the free enzyme activity measurement. Now, the fourth step is the enzymatic activity evaluation upon pH, and in this sense, the fifth one is going to be the enzymatic activity evaluation upon temperature, because as I mentioned before, these are going to be part of the main goal of this project. Now, the sixth one is for the microreactor design, which is going to be through AutoCAD. And then we are going to perform the preliminary test of the encapsulated lacase in the microreactor. And finally, the eighth step, which is the last one, is going to be the microcapsules characterization before and after wastewater treatment, which means like before to be in the microreactor and after it. And after that, sorry. Okay, so for the results of the first step of our methodology, the design and the manufacture of the microfluidic device was carried out following the procedure described by Campagna et al. So a flow-focusing approach was selected to manufacture the polymeric capsules. And this was because of the facility it offers to maintain great control over the size of the microcapsules, mm, which is probably due to the channel width of the microsystem's final part and its shape itself. Also, the fabrication of the microsystem was carried out using laser cutting techniques and polymethyl methacrylate as substrate for the manufacture of the sheets that would make up the microfluidic device. Also, in the figures, we can see the dimensions and the total size of the final microsystem that were also used by Campagna et al., as I mentioned before. Now, for the second step, the parameters configuration for microcapsule generation. As we can see in the table, three different flow rates for the continuous flow and two different ones for the discrete one were tested to determine the most efficient ratio to obtain the desired size of the capsules, where it was determined that the most suitable ratio for the production of capsules was 80 millimeters per hour for the continuous flow and 0.7 for the discrete one. And as we can see, in that way, using that ratio, we can obtain an average size of the capsules of 1,100 micrometers, which is like the desired size in this case. Now, as we can see in the real-time video right here, every capsule looks exactly as the same one. Exactly the same as the previous one, which, as mentioned before, was one of the goals for the experimentation. Finally, we could divide the third step of our methodology in two different ones, the enzyme activity evaluation and the enzyme encapsulation itself. So first, free enzyme activity measurements were performed by spectrophotometry, measuring the absorbance for 1 minute at 436 nanometers, and one activity unit was defined as the amount of lacase needed to oxidize 1 micromole of ABTS per minute under the assay conditions. Also, enzyme activity was expressed in terms of units per liter, following the equation shown in the slide. And the activity obtained for the enzyme was 560 units per liter. We also encapsulated the enzyme successfully, following the flow rates shown in the table right here. But we are still up to measure the immobilization ratio because of an unforeseen experimental error. For the future work, we still have to perform the enzymatic activity evaluation upon pH and temperature, design the microreactor, and also perform the preliminary test of the encapsulated lacase in the microreactor, and of course, characterize the microcapsules before and after wastewater treatment. Here I'm showing some references used in this presentation. And now, thank you so much for your attention.